Good day, folks. I'd like to talk to you about the inverted dipole effect that I've noticed with the PEG cells. I've talked about in my previous videos, but sometimes just showing a demonstration is difficult to understand, so I'm going to try and draw what's happening here. So here's the PEG cell, and this is your plus electrode and your minus electrode, and this stuff here is the dried up PEG, which is completely electrically isolated, no closed loop when you measure here and there. Okay, so what I've been doing is I've been putting my series cell like this going into another cell's plus here, and then the negative out here connects here, and let's say this is my cap dump, and it charges the cap here with the combined potential of the both cells. This is pretty easy to understand. It's a typical series DC circuit at this point, but we're limited by whatever the potential of the electrostatic displacement between the two electrodes here, that we're getting the, whatever it is the PEG puts out, 0.5 volts or so, and these two apparently combine. So let's say that the 9-volt battery is putting 9 volt in, and it would be plus that 9 volts, so you'd get around 9.5, right, once it's in the series. But you'd be limited at whatever this one here can provide, which is fine. This is what we're looking for. So again, it's not a free lunch, folks. There's always going to be a small energy that's need to be used to align the dipoles, okay? So that's the trigger. So basically here, when we put a series cell, this is going to become your trigger. Now, it's not the same kind of current as traditional. Like, for example, a 9-volt battery that's open dipole, essentially not connected, will naturally drain. It might take months on its own, and then it flattens out, right? Now, let's say, I'm just making this up now, let's say it takes 30 days for it on its own to get to like near zero. Well, if we're using it for electrostatic dipole alignment, it might take, 29 days instead to drain. You see, there is a subtle amount to create the dipole, right? But as soon as the dipole is aligned, it's very minimal to keep going. It's an electrostatic effect. So of course there is a loop that's happening, but it's not a traditional lossy closed loop against itself electrically. Now what happens in the PEG cell is you've got its own electrostatic potential, and the cell does something very unique. If it's left open and you were to measure it, and I've done this earlier videos and others have demonstrated as well, you put your scope on here and you can actually measure the displacement. It comes in through transient ACs of random, very sharp spikes. The scope can't even get a lock on them. They're all random, and a lot of those spikes are so sharp the scope doesn't even read. But what essentially is happening at random frequencies at all times, that's the electrostatic displacements, those little sparks that are going from one to another here, and that's creating that ping pong action. So now, let's say where it goes up to, so maybe there's peaks of around 0.5 volts that we're not seeing in there. It's happening really, really fast. The dielectric is acting as a capacitor and is charging up at the same time. And when we put a load on there, that filters it out. And we see this as a low level 0.5 DC, let's say 1 MA, through this action that's happening very real in the background here because of the electrostatic effect. So what I'm getting at is, yes, the cell does self-oscillate, but it's completely random, and there really is an EM interaction going on here between the ping pongs inside the cell, but it is self-regaging abilities. And what happens with this is, at the magnetic, there is no loss between the interactions. So not only is it a low loss system, but it is a self-regaging because it can self-regage its electrostatic potential. So not only is it a regular battery that shows a potential, but it has the ability to keep resetting that potential because of the natural electron count at each plate here. One of them is always going to be a donor, one of them is always going to be a receiver based on the natural count that is available at all times based on the element. So there's your free-flowing source right there that automatically regages with that low current here. So great, all we have to do is stack our cells, bring it up to whatever voltage we want, 110 if we want, and we're good to go. You know what you got to do with that? There's your fountain of unlimited energy in Tom Bearden terms, by keeping the dipole open. But I didn't see this effect right away because I was using half-dead batteries that were around 5 or 6 volts, and I had 2 of them in series here. So when I originally turned this on, I saw something like, 10 volts coming across with my peg cell, and I called it a day. I said, yeah, it's working good. And of course, with the effect, it still was pretty good. Now, of course, what happens is I've realized that even though we talked about the inverted dipole electrostatically in the comments, I was thinking this was more the quantum, very, very localized effect kind of thing. But once I actually measured the cell in the video, in the previous video I showed you, all of a sudden when there's any kind of flow, it doesn't matter what direction, this cell goes from 0.5 to minus 10 volts, like instantly as soon as you put the load here. This is great, this is wonderful, that this basically came for free just through the displacement. And once it's established, it's there, and that potential builds in series. But now you see we have, if you got minus 10 going in, it flipped the polarity. So what I'm getting at is I was getting nowhere near what I could be getting. So that's why I said the dummy I am. I decided once I've noticed this, okay, so instead of going from the negative of the cell to the plus of the cell, let's go from the negative of the cell to the negative here and go out plus here. So on each end you've got two pluses, but that then creates a new positive and negative for the cell based on the potential differences. So as is without a load, you basically get, your 0.5, your 9 volts minus 0.5, that would be the series, but we don't have a load connected to it. The magic happens when you try and complete the loop. All of a sudden, this does a sudden inverted dipole effect, and this goes minus. Not only does it flip, but it flips and gives you that potential all of a sudden. So that's why I decided when that happens, all of a sudden, this flips internally, so this becomes plus, this becomes minus, then the hookup is right. So all of a sudden in my meter, it has a maximum of 20 volts, I was peaking at 20 volts and it would error out because all of a sudden it combined those two potentials for free. So now basically, like I had, well, my version here was the 12 volts capacitor. But what happened is it combined those two potentials now, and then I had over 20 volts for free. This is very great. This means a lot. This is excellent if you understand what you can do with that. So this is what I was trying to get at. So of course, what I was explaining, there's no free lunch, but you'll run a very, very long time by using your series just to bring up the electrostatic potential. And yes, there is going to be electrostatic displacement within the peg cell itself, but that's basically a localized effect on its own, and the peg cell balances that out and makes up for the loss. So this is why I say this is if you were to ask what this does as an electrical device, the peg cell, the closest thing, the definition would be a nonlinear ferroelectric negative resistor, as weird as it sounds. The nonlinearity is because the state of the peg cell changes depending on if it's got potential or not. And the ferroelectric is that response you get the inverted flip. Now what's funny in this, folks, is like 3 months ago when I was exploring the peg cell, I indirectly noticed that this effect and talked about it. I even showed you on the scope. I said, something funny, folks, pulse the cell in reverse, so a negative pulse, and all of a sudden I get back a much stronger positive spike. I figured it was just a spike because the scope only sees the spike. But if I would have paid more attention, I would have actually realized as long as I keep the potential on, this would have remained a much higher DC. So indirectly, I saw it without realizing that it wasn't just a pulse, you see, but the cell had that inverting effect and gives you back a much greater, as we're noticing here. So this is a great effect to have. And in negative resistance, what I mean is, of course, every battery you can say it will, because it puts out, will be seen as negative resistance, but it's not true negative resistance because it just basically fools the meter because the battery will eventually drain. The difference here is between the electrostatic potentials. It's able to re-gauge itself and give and keep being a giver of the circuit instead of a receiver. So this device acts as a negative resistor in the sense that it can re-gauge and make up for its own losses and contribute to the circuit at the electrostatic level. Then you can get your pure potentials. You know, once you start getting to 100 volts or so, it gets very interesting. Large capacitors charge very fast. You can dump this. You could have a small switch and simulate the AC frequency you want and actually get some wattage out of it if you know what you're doing. So this is all I was trying to get at, is this is a very interesting system, and we should be really using the PEG as a electronic device, I believe, and we need to explore more of this. Now, the boring part for me is I have to sit here one day and actually plot the VI curves here and the nonlinear ferroelectric responses and plot all that and try and find the sweet range. So the whole idea would be to intentionally operate the PEG in that sweet spot once we actually know, because we're noticing the effect, but there's going to be a sweet spot somewhere in the VI and the resistance and everything, and it all shifts because it's non-linear. But you're going to find a range there which is the optimal, the sweet spot. So that's going to be a lot of work, and unfortunately I don't have to. Those who are always asking if they can help me out, here's one thing. What I will need is a lab grade power supply. It doesn't have to be high current, just so you can be fine, 100 millivolts at a time and go all the way up to 24 volts or so, because I'm going to have to plot the curve on this thing and find the sweet spot, but I need that precise equipment. And ironically speaking, I do have power supplies and variable, but nothing to this precision where I could actually make a proper VI curve and plot the resistance and everything and the non-linear ferroelectric responses and what range is the maximum and all that. It has to be done, because if we're going to take this seriously and understand how we want to integrate the PEG in everyday electronics, we're going to have to find those sweet spot zones. So that's going to be next, because we really got to get to the fine details here, and it's relatively simple. It's just a matter of doing the work. But I just wanted to show you folks here on the board what's going on and how to take advantage of that. So with that said, folks, I'm gonna leave that with you to think about, and I'm looking forward to your comments. Thank you for watching.